Welcome to chapter 4. We are finally out of chapter 3 where we were there for 9 sections or something like that. Um, so chapter 3 was all about calculating derivatives, all about finding derivatives. Talked about the product rule, the quotient rule, the chain rule, the constant multiple rule, the inverse function theorem, the how to take derivatives of exponentials, logarithms, all these things for finding derivatives. And now chapter 4 is all about what can we do with that. And that's how we're going to start in 4.1. Now 4.1, related rates, we'll talk about what that means in a second. But this entire section is contained in the first video. All the section is just this first video, and the rest of the videos are just to help you. But there's no new material after the first video. Okay, so without further ado, we're going to get started on that note, and hope you're ready. So there's a lot of problem solving in this section. There's going to be 30 different kinds of problems. You can't cover it all. We're just going to try to show you an approach so that you can apply that approach to different problems. Okay, so let's start with a little introduction about related rates. I'm not going to actually write anything there, but you could if you wanted to. We're going to start with an example. Example 1. A spherical balloon is being filled with air at a constant rate of 2 centimeters cubed every second. So the volume is increasing. The volume is in centimeters cubed, and it's increasing by 2 centimeters cubed every second. The slope, if you will, is 2. So how fast is the radius increasing when the radius is 3 centimeters? So let's get a picture of what we've got here. So we've got some sort of some sort of sphere. And this sphere has some radius. Sphere has some volume. What's the volume of a sphere? Let's say hypothetically, you don't remember. You can just say, okay, volume of a sphere. What is it? And you get, okay, it's 4/3 pi times the radius cubed. So we're going to write that down. 4/3 pi times the radius cubed. Let's see. How fast is the radius increasing when the radius is 3 centimeters? We're curious about when the radius is 3 centimeters. And we know that the balloon is being filled with air at a constant rate of 2 centimeters cubed per second. So the rate is the derivative. But be very, very careful. I'm going to write something down. It's going to be wrong, so don't write this down. You say, okay, constant rate of 2 centimeters per second means that the rate of change of the volume is 2. And that's mostly true. But this is wrong, what I've written down. This is the derivative of the volume with respect to the radius. And now normally dV/dr would make sense because we have a V and an R here. But let me slightly change this volume equation to be more accurate to our situation here. This is just an introduction here. We'll do a more formalized step-by-step process for these sorts of problems in the next video. I just want to introduce some concepts. This sphere, this balloon is inflating over time. The volume is a function of time. The volume is changing over time. So instead of writing V, let's write it as a function. V is a function of time. 4/3 times pi. Well, the radius is also changing over time. Right? This balloon is getting bigger. This radius right here is growing over time as well. So not only is the volume a function of time, the radius is actually a function of time as well. So these are multiple functions of time. And that's what related rates is all about. Say, it's just saying, okay, instead of just having area formulas, volume formulas, any formula that you can think of, let's have these same formulas, but now everything's changing over time. So when we're saying that the volume is increasing, at a rate of 2 centimeters cubed every second. Second right there tells you that we must be taking the derivative with respect to time. So the derivative of the volume with respect to time is that 2 centimeters cubed every second. All right. So what are we asking? What is the problem asking us to do? How fast is the radius increasing at this point? So it wants us to find the rate of change of the radius with respect to time. This is what we want. Sometimes in previous classes, my math professor would say, this is what we want to find, and they would abbreviate that WTF. If you want to abbreviate that and write WTF on your quizzes and notes, that's fine with me as well. This is what we want to find. We want to find the derivative of the radius with respect to time. And this right here, everything I've written down so far, this is the challenge of this section. Once you get to this point, it's actually a 3.8 problem. Once you get to this point, it's just implicit differentiation. This is the hard part though, getting here. And this is the part that we're going to spend most of our time on in these videos, talking about how to approach. Okay, so this is all the information that we're given. And once you have this information, it's much easier to solve the problem, but getting here can be tricky. And so that's my claim. And so if this is what we want to find dr dt. How are we going to get to a derivative? We're going to have to take the derivative. We're going to take the derivative of both sides of this equation. And specifically, the derivative with respect to what? Because there's a lot of options. We could take the derivative, we could take the derivative with respect to the volume. We could take the derivative with respect to the radius. We could take the derivative with respect to time. We could take the derivative with respect to my happiness. There's a bunch of derivatives that we could take. Which one makes the most sense here? Look at what we're trying to find. And how are we going to get there? We want dr dt. Which of those things on the left is going to give us a dr dt? We want to take the derivative with respect to time. That bottom one. So we ddt both sides. On the left-hand side, we're taking the derivative with respect to time of our volume. On the right-hand side, we're taking the derivative with respect to time of 4/3 pi times r of t cubed. Okay, so let's start with the left-hand side. This is implicit differentiation. What is the derivative of a volume function? Well, we don't know. Let's just call it v prime of t. Whatever the derivative of the volume, right? These just mean the same things. Like when we first introduced the derivative, right? We said the derivative of f is f prime. Well, this is the same thing, but instead of calling our function f, we're calling our function v. And on the right-hand side, we can use the constant multiple rule. This is just a constant, right? We can bring constants out in front of a derivative. We're going to have 4/3 times pi. And then we have to take the derivative of r of t cubed. That's going to require the chain rule. Take the derivative of the outside function, 3, subtract a power. Inside function stays the same. Remember your implicit differentiation. And we multiply by the derivative of that inside function. And again, the derivative of r of t is just r prime of t. Or dr dt. It's up to you. So again, we've written it a couple different ways, but just to be very clear, dv dt, that's the same as v prime. dr dt, that's the same as r prime. One is Leibniz notation, one is that Newton's notation. So once we've taken the derivative of both sides, we pretty much know everything we need to know. This is 2, right? We're curious about this situation when the rate of change of the volume is 2 centimeters cubed every second. So we replace it. That is just 2 now. equals 4/3 pi times 3. Oh, let's cancel those 3's actually. I like canceling. There's just 4 pi times r of t squared. And specifically, we know the radius is 3 centimeters right now. So we're looking at this question when the radius is 3 centimeters. Replace that radius with 3 centimeters. It's still getting squared. And we're multiplying by r prime. And r prime is exactly what we want. Let's write it as dr dt. Let's try to be a little bit more consistent. Well, how do we find dr dt? Now it's just algebra. Solve for dr dt, just like we did in implicit differentiation. So this just turns into 2 equals, this becomes 9 times 4, just 36 pi times dr dt. Divide both sides by 36 pi, and you're going to get dr dt is 1/18 pi, which is approximately equal to something. 0.0177. That is the rate of change of the radius, which is given in centimeters. My m has one too many humps. Rate of change of the radius in centimeters over time in seconds. So if the volume is growing, if the volume of a sphere is growing at 2 centimeters cubed every second, then when the radius is 3 centimeters big, it's growing pretty slowly. Who's blowing up this balloon? An ant? All right. That's fine. The volume's not increasing very fast. That's what this video is all about. This is just an introduction. In the next video, I'm going to show you a step-by-step process so that you, too, can do this long and somewhat convoluted process, depending on your perspective. Stay tuned, and I hope you're ready for some more applications. If you'd like to, no, I won't say that here anyway. Bye-bye.